Alright, welcome to the introduction of chemistry. Let's go ahead and define what chemistry is and jump right into this. Chemistry is the study of the composition, structure, and properties of matter and what changes it undergoes. That's from your notes. A broader definition might be changes in energy, because it requires energy to go through any kind of change in structure or properties of matter. In order to observe these changes, we need special instruments, because in chemistry we're dealing with atoms and molecules. So we have to have some special instrumentation to do that. In your biology class you would have used a microscope. Even a microscope is not powerful enough for us to see something at the atomic level. So a lot of chemistry is theoretical and concept driven, because it's over things that we don't actually have technology good enough yet to see. So the way that we do see things is by running chemical reactions. Our study of the periodic table allows us to have a predictive element to chemistry, so that we can predict what's going to happen and then test and see if it does happen. And we've done a lot of that over the many years of chemistry. And so we're pretty good at figuring out what's going to happen before it does, and that leads us to be able to create some pretty awesome things. I always say, what in the world is not chemistry? Because there's literally nothing that you can put your hands on that hasn't been either touched by a scientist first or isn't composed of something to do with chemistry. So look around the room that you're sitting in right now and come up with some things, 5 things that are related to the study of chemistry. And go ahead and pause the video or something, write down what you think, and then come back and I'll have my 5 things written down. Alright, so my 5 things were air, me, clothes, TV, and food. Maybe we shared some in common. Maybe you came up with some pretty cool ones that I missed out on. So I'll go ahead and briefly explain why I chose what I chose. Air is made up of oxygen and nitrogen. That should have a 2 there. Nitrogen and carbon dioxide, and then it's got some other trace elements in there. So boom, right there we've got different elements. Me, I'm made up of proteins, which are compounds. I've got sugars inside of me, which are compounds. I've got fats, probably a lot more than I should. Those are made up of compounds. All of those things are part of chemistry. That looks like it says farts, but it's really fats. Alright, clothes. I'm wearing a blue shirt, so I've got dyes in my clothing that make it look blue. Those are chemical compounds. The fibers of the clothes themselves are made up of atoms. TV is just a flow of electrons. And food, obviously, is basically this same thing right here. It's what I'm made up of. You eat food, you break it down, and you reassemble its components into you. Alright, so those are my 5 things. Let's move on. There are 6 main branches of chemistry. We have organic chemistry. Anytime you see organic, you need to think of the word carbon. Okay, so you are an organic being because you're made up of carbon. Just a minute ago I said I was made up of proteins and sugars and fats. Guess what? You are too. And proteins and sugars and fats are organic compounds because they all have carbon as a base to them. Inorganic, alright? If organic means it does contain carbon, then inorganic means it does not contain carbon. So those would be things like salt, alright, like sodium chloride and water, stuff like that has no carbon in it. And also, strangely enough, carbon dioxide, the stuff that you exhale, even though it has carbon in it, it is considered an inorganic compound. And I really don't know why, actually. So maybe I'll do some more research, or you can, and let me know. but that is not considered an organic compound, even though it's got carbon. Physical chemistry really talks about how the molecules move in the test tube, in the beaker, in the air, and how they collide with each other and how much energy they exchange, and it's got actually a lot of physics, particle physics, to do with it. Analytical chemistry is if you run a business and your business produces some kind of chemical waste, there are a bunch of regulations, state and government regulations that say, you can only produce this much, and when you dispose of it, it has to be done a certain way, and blah, blah. So you might have to take that stuff to a lab and see what the concentration of it is, or maybe you don't even know what it is, and that lab identifies what you have there. Biochemistry, that is one of my favorite parts of chemistry. It combines biology and chemistry together, so it studies living things and the chemistry that happens inside of them, namely the metabolism. See if you can remember what that means. Metabolism and catabolism. Do you remember what that means? So metabolism is the breaking down of nutrients, and catabolism is the building up of nutrients. So when you eat something, you metabolize it, and then your body goes through catabolism to create, your blood cells and your skin cells and hair and all that kinds of stuff. And then theoretical chemistry is where you use a lot of modeling and computer simulations to figure out what the molecules would do, how they would behave, and be able to try and predict some things about certain reactions and processes without actually being able to do anything yet. And that might be because we don't have the resources or the supplies, or maybe the technology is not good enough to be able to work with a certain material yet. For example, some radioactive elements only exist for nanoseconds, and then they decompose into other elements. So we can't play with them because we don't have a long enough period of time, because they break down so quickly. So theoretical chemistry would have to do a lot with that. Alright, chemicals are any substance that has a definite composition. Alright, definite means it doesn't change. Alright, so make sure that you jot that down, that doesn't change. So glucose, you remember that from photosynthesis, hopefully, C6H12O6. Water, like I mentioned, salt, hydrogen peroxide. All of these things are always the same. It's always going to be 2 hydrogens for every 1 oxygen, and that is always going to be water, period. Okay, so anything like that is going to be a chemical. Mass is a measure of the amount of matter that something has. So what is something that has mass? Alright, you write down anything that you think has mass. And I'm going to put air. And you might be wondering, why would you say air has mass? I can hold my hand out and I can't feel any air sitting in my hand. Well, it's not based on what you can feel, it's based on if it has mass. And oxygen and nitrogen and those things, they do have mass. It's just so light you can't feel it. Alright, matter. Anything that has mass and takes up space. So I could again put air if I wanted to. I could put something different. I could put my shoes. That's made up of matter. I guess a good question to ask would be, what is not made up of matter? What do you think is not made up of matter? The answer is energy. Energy is not matter. So forms of energy like light and sound and heat, those things are not matter. So that's important to recognize. Um, Atoms are the smallest unit of an element that still maintains all the properties of that element. Okay, so let's take a look here. For example, hydrogen. Okay, the smallest amount of hydrogen that I can go to is 1 atom. Alright, if I try and go smaller than an atom of hydrogen, then I get into the electrons that are circling around, and I get to the protons and the neutrons. Now, actually, hydrogen doesn't have any neutrons, but it does have 1 proton and 1 electron. Well, hydrogen's electron is the same as the electron for any other element on the periodic table. There's no such thing as a hydrogen electron. All the electrons are the same kind. And electrons don't behave like hydrogen. They behave like electrons. So that's why I'm saying to you that if you try and go smaller than 1 atom of hydrogen, it's not going to behave like hydrogen anymore. You are the smallest unit of you. If you try and go smaller than you, maybe you get a haircut, the pieces of hair that fall on the floor aren't you. They were just pieces of you, and they won't behave like you. They can't talk, they're not your same height, they have no brain function, and you do. You are the smallest unit of you. So hopefully maybe that helps to make some sense there. An element is a pure substance made up of only one kind of atom. Alright, so we could put hydrogen in here again. And now we can see we have a little bit of a problem here. Notice that an atom and an element, I was able to put the same example, a hydrogen. Alright, that leads people to use the word atom and element interchangeably. And for the most part that's okay, but you do need to understand that they are actually two different things. Alright, compound is a substance that's made up of 2 or more elements. So, like water. Alright, we have a hydrogen element, or two hydrogen elements, and 1 element of oxygen. Alright, so that gives us a compound. Here's a good diagram of how matter breaks down. Okay, so matter, something that has mass. Alright, it can break down into a pure substance or a mixture. We're going to focus on the pure substance side for a second. Okay, pure substances can be classified as elements or compounds. Remember, element is a single atom, and a compound is 2 or more atoms put together. Okay, to get from an element to a compound, a chemical change has to occur. Alright, let's talk about mixtures. Alright, you can have a homogeneous or heterogeneous mixture. Remember that homo means same, and hetero means different. Okay, so if we look here in this example, we notice that from top to bottom, looking in this little window here, from top to bottom we have an even distribution of these single orange and these doubled up greens that looks the same all the way throughout. On the heterogeneous mixture, when we look in this window, you can see there's a definite separation. It does not look the same in this region of space. There's a chunk of stuff up here, and there's a chunk of stuff down here. So it's separated, it's organized looking. This one is all scrambled up, all mixed together so that the whole thing looks the same throughout, and this one looks different throughout. You can definitely see regions. So let's give some examples. What do you think are some examples of a heterogeneous mixture where you can definitely notice the different regions? Okay, so like a chocolate chip cookie might be a good example. Alright, or a salad, and I have no idea how to draw a good salad on here, so I'm not going to attempt it. How about a homogeneous mixture? What do you think a good example of that would be? Okay, so maybe something like a glass of Kool-Aid. That's my cherry flavor Kool-Aid there. Alright, it looks the same from top to bottom. Alright, okay, now let's look at this. In order to get from a pure substance to a mixture, we go through a physical change. Alright, so let's quickly talk about this Kool-Aid down here. Inside the Kool-Aid we have water, and we have sugar, and we have some Kool-Aid powder, and I don't know the formula. That's a special secret, so I'm just going to write that in. So all of these are compounds, alright? Remember, a compound is more than one element put together. So that's got more than one element, that's got more than one element, and I assure you that one does too. So all three of these compounds were all put together inside of this drink here, okay? And that created a mixture. So let's get a simple little definition here. A compound, we said, was two or more elements, and a mixture is two or more compounds. Okay? Mixtures are made up of pure substances. Okay? So if you get two or more of these compounds, like that's water right there. You get water and sugar, that's another compound, and so on and so forth. You can get a mixture. You can get different kinds of mixtures. Alright? So here's kind of the wording from your notes. It's a blending of two or more kinds of matter. Really, I think the very best definition is what I just told you, is that it is two or more compounds. Alright, so if you remember that, you should be good to go. Alright, a pure substance, this was the left hand side of that chart, it has a fixed composition, and that's because it's made up of compounds or elements. Alright, and it differs from a mixture because it keeps the same properties. Alright, Kool-Aid is made up of water. If you drink water by itself, it doesn't taste like cherry flavored Kool-Aid. If you don't put the sugar in the Kool-Aid, you just mix the powder with the water, it's bitter, it's not sweet. Alright, that sugar, even though you added it to the water in the Kool-Aid, the property of sugar to be sweet didn't go away. It kept its same property the whole time because sugar is a pure substance. Alright, so go ahead and you can read over the rest of that on your own. Elements here can't be decomposed into simpler substances, and we actually covered that when we said that an atom is the smallest part of an element that still retains all the properties of that element. You can't go smaller than that. Alright, this is an important part. Properties of our different compounds and mixtures. You have extensive and intensive properties. Extensive properties depend on the amount of matter. That is going to come up in a test question, I guarantee you. So you need to devise some way to remember that extensive properties depend on the amount of matter. Intensive properties do not depend on the amount of matter. Alright, I don't have any tricks to help you remember that, so you're going to have to devise your own on that. Usually I've got some tricks. That one, I haven't found anything yet for you. Alright, then you have physical and chemical properties. Alright, and matter has both of those different properties. A physical property would be its weight or its color, its shape. And you can't change that by doing something to the item. So for example, if I told you I was wearing a blue shirt, alright, if I cut the arm sleeve of my shirt off, the color won't change. The shirt sleeve will still be blue, and the rest of my shirt will still be blue. They just won't be connected to each other anymore. So I can't change that physical property by doing something physically to the object. Chemical property is when I actually transform it from one substance to a new substance. Alright, so if I take a piece of paper and I set it on fire, it turns into carbon. That black ash is just carbon, and it's not paper anymore. It doesn't have the same properties as paper anymore. So it's a whole new thing. The smoke is carbon dioxide that was released. So you get some new compounds out of it and destroy the old compounds. They are changed, transformed into something different. Almost done. Changes in matter, alright? I just said about physical properties and chemical properties, and you can affect those by a physical change or a chemical change. So let's look at physical change first. It does not involve a change in the identity of the substance. Again, cutting off my arm sleeve, the fabric is still fabric. If I took a piece of paper and ripped it in half, both halves are still paper, so I don't change the identity of the substance. Dropping a glass and it breaks into shards of glass, all of that stuff is still glass. And getting your hair cut, you didn't stop having hair, it's still hair. Chemical bonds are not broken in a physical change, okay? And it always includes a change in state, alright? If you I guess I should rephrase that. Not all physical changes are a change in the state of matter, but all changes in the state of matter are physical. So if you go from a solid to a liquid, or a liquid to a gas, you are doing a physical change. Okay, so if I take an ice cube, alright, and I put that ice cube in a frying pan, and I turn on the heat, and it starts to melt and give me liquid water, and then I keep heating it up, and that water then starts turning into steam, so I get these little gas bubbles. That's what that is. So I get gas rising. That's a change in state from solid to liquid to gas, and that is not a change in the chemical. Alright, ice is just frozen H2O. Liquid water is still H2O, and steam, which is gaseous water, that's still H2O. I did not change the chemical. Alright, now let's look down here at chemical change. That's if I actually do change the chemical. Iron, which is on the periodic table, Fe. When it rusts, you'll notice it changes color, and the reason it does that is because it's a whole new compound. Rust is where we add in some oxygen into that. So that's actually the formula for rust. Alright, so you can change it, just like I said, setting the paper on fire, it changes it into carbon dioxide and some carbon, and there's water vapor and all kinds of stuff like that. How will you notice that a chemical change has occurred? That's what I have these 5 things down here for. The formation of a precipitate, alright? A precipitant is this, okay? When two liquids come together to form a solid, here's the definition right here. When two liquids come together to form a solid, that's a precipitant. Alright, so this is an example of a precipitant. It is different from precipitation. Alright, that's weather. Alright, rain and snow and sleet and all that. So don't get those words confused, please. Another way that you could tell that a chemical change has occurred is if the color changes. Again, I told you when something rusts and it takes on that red type color, that's a change in color. That kind of is a hint that a chemical change happened. If a gas is produced, that's a hint. If the temperature changes, either hot or cold, and if it smells different, if the smell changes. Now, that doesn't mean that if one of these things happens, boom, it's automatically a chemical change. Notice up here, if I take this ice cube and I heat it up and I form a gas, right there, production of a gas. That might lead you to believe that it's a chemical change, but it's not. Remember, changes in state are physical changes because it's still the same compound. So even though one of these things happens, doesn't automatically mean that it's chemical. What if I dropped food coloring into water? That changes the color, but does the water stop being water? No, it's now just it's water, and then the dye molecules are mixed in, so you can't distinguish them. But those two things are still in there. I didn't actually change either of them. I just mixed them up. What kind of mixture would that be? Heterogeneous or homogeneous? What do you think? Good, that's a homogeneous mixture. when I heat the water up, the temperature changes. Again, it's a physical change, it's not chemical. So these are just kind of guidelines, they're not for sure things. Alright, the last thing for this video is how to recognize and write a chemical reaction. We have the reactants, or the beginning things, located on the left-hand side of what we call the reaction arrow, and the products, the things that we make, are located on the right-hand side of the reaction arrow. So here are our reactants, and here are our products. Okay, notice both of these are compounds, so that one's a molecule there. So, but we could have single elements, and we'll get into all of that later, but you do need to know for sure that reactants are on the left, products are on the right, and that this is called a reaction arrow. We're going to talk about the family names for the periodic table. The periodic table is arranged into groups or families which move up and down, and they're arranged into periods or rows which move left to right. We can use this as kind of a coordinate system. So if I wanted to talk about copper, then I would talk about group 11, row 4. And the element that's in group 11 and row 4 would be copper. All right. All the elements within a group have similar properties to each other because they all have the same number of valence electrons. And remember, valence electrons from your biology class, if y'all talked about that, if that's the nucleus, and let's say I'm going to draw hydrogen. So I've got one proton in there, and then a valence electron is the electron that's in the outer energy level. Okay, and hydrogen only has one energy level. So all of the other elements in group 1 here, they only have one electron in their outer energy level, but they have more than one energy level. Hydrogen has one energy level, lithium has 2, sodium has 3, and so on and so forth. Alright? So let's go through the family names. Anything that is in white on this periodic table, those are all non-metals. Okay, so stuff that's not made of metal. Then the rest of group 1 here is what we call the alkali metals. Group 2 are called the alkaline earth metals. So on your periodic table that's in your notes, you need to make a change there. So right there, we need to change this so that it says alkaline earth metals. Alright? Okay, so then the next thing that we have are our transition metals, which is all of this stuff in the middle here. And you can color your periodic table however you want it to be. That doesn't make any difference to me. I'm going to change my pointer real quick so that, and it's going to be weird, but I'm doing it so you can see over the top of this purple looking color. Alright, so all of these are transition metals here. Okay, then we have our pore metals, which are over here in gray. Pore metals, on here they're called other metals, so you need to make a change on that one as well and make them say pore metals. Alright, that just means they don't do a good job of acting like other metals do. Okay, then we have our metalloids, which are these in yellow here, and they behave, sometimes they have properties of metals and sometimes they have properties of non-metals. And what I need you to do is add in a stair-step line here. Alright, and I'll draw that in for you so that you can add it into yours if you haven't done that already. But you're going to add in this stair-step line all the way down so that we've got these metalloids on either side of that stair-step line, all the way over. Okay. Then we've got our nonmetals here in white. Okay. I'm going to change my pointer again so that we can see more clearly. Then we've got halogens here in the second to the last column. These are our halogens. Okay. And in the last column, we have the noble gases. Alright? They don't really interact with anything. That's why we call them noble. They're like snooty. They don't really interact with anyone because their valence energy level is all full. So they don't need to react with anything. And then we have our last group down here at the bottom. These are called the rare earth metals. Alright? And I want to make a special note about this right here. Notice that we have these two guys up here in the periodic table, but they're colored the same color as these. They should not be. These guys right here should be the same color as our transition metals. I don't know, whoever made this periodic table is wrong, but these should be the same color as your transition metals. And then these down here should be their own color. Sometimes on periodic tables you'll see these two elements up here in the table, and sometimes you'll see them in front of the table. So here's an example of that, where you'll see a periodic table where lanthanum and actinium are pulled down out of the periodic table and they're placed down here with the rest of the rare earth metals. Okay? And the reason for that is because from element 58 to 71, that's called the lanthanide series, and it's named that because it starts with lanthanum over here. And this is called the actinide series, and that's because it starts with actinium there. And so on this periodic table, we've just named those series for you and then left these up here in the periodic table. Alright? But again, they should not be colored the same as the rare earth metals down here. They should be colored just like the transition metals. Okay? Alright, let's move on. We said that groups are the ones that are vertical, that move up and down, and periods are horizontal, they move left to right. Okay? And we can split the periodic table into two groups. If we look at this again, notice, look at this stair-step line over here. Okay? Everything to the left of the stair-step line was a metal. Alright, look at the names. Alkali metal, alkaline earth, transition, rare earth, poor metals, metalloids. Alright, all the stuff to the left of this stair-step line, all of this over here, are metals. And then all of the stuff over here to the right of the stair-step line are nonmetals. Okay, you've got gases, which aren't metals. Halogens are usually gases, so they're not metals. Then you have your nonmetals. These are gases also. And then these yellow ones here, those can behave like metals sometimes, and sometimes they behave like nonmetals. Alright? So in general, everything on the left of the stair-step line is a metal, and everything to the right of it is a nonmetal. So if we're looking at our types of elements here, and we talk about metals, we can say metals are conductors. Alright? And a conductor allows energy to flow freely. And nonmetals are poor conductors, and that is a special name. If you're a poor conductor, you're called an insulator. Alright? And so an insulator restricts the flow of energy. Alright? Okay, we said that metalloids straddle that stair-step line, alright, and that sometimes they have characteristics of metals and sometimes they don't, alright. All the metals, or metalloids, excuse me, are solid at room temperature, so none of them are gases. Silicon is a good conductor of electricity, but an insulator of heat. And that's a good thing for us because that's what our computer chips are made out of. Oh, I misspelled that. So because of that, because it has a property of a good conductor of electricity, but an insulator of heat, we use that in our computers because we don't want our computers to get overheated, but obviously they need to be able to conduct electricity. So that's a cool thing there that we take advantage of because that's a metalloid. And then we said that noble gases don't really react with anything because they have a full outer energy level. Okay? Now we're moving into the calculations part of chemistry where we start messing with some actual numbers. Before we do that, though, we need to go back and review the scientific method, which you should have had in biology. You're going to need to know these 6 steps of the scientific method in order for a quiz. All right? And when you take that quiz, I'll accept several things here, like where it says question, you could write state the problem, or you could just write problem. I'll accept either one of those. Here where it says hypothesis, you could say state the hypothesis. So these little dashes mean ditto, all right? State the hypothesis. Experiment, or you could say test the hypothesis. And then collect data and conclusion. And those are pretty self-explanatory. You need to write those. Okay, we have a couple of different types of observations that can be made in science. Now, observations mean that you have to collect some kind of data, all right? And the data can either be a quantitative or a qualitative data. Now, quantitative has that root word of quantity, all right? So when you think of a quantity, you should be thinking of a number, all right? And that's the type of observation that quantitative data deals with, numbers, okay? So there are 9 cats across the street. That's a quantitative observation. Qualitative observations are descriptions or characteristics, all right? And so that would be something like there are black cats across the street, okay? Some kind of a characteristic is given about the thing that you're observing. Or you could combine both of those together and we could have something that says like there are 9 black cats across the street. And then that observation has both types of observations in it, okay? All right, next thing we're going to talk about is a hypothesis, and you are never allowed to call a hypothesis an educated guess again. Never, ever, ever. That's what we tell you when you are children, so that we can introduce the concept and you'll still be able to understand it. But now that you are grown, you need to remember a hypothesis is a testable statement, okay? The way that you're going to make sure that your hypothesis is always a testable statement is to make it an if-then statement, all right? So for example, if I flip the light switch down, then the lights will go off. That can be tested. I can get up, go across the room, flip the light switch down, and see if the lights do turn off, okay? And if they do, my hypothesis was right. And if they don't, my hypothesis was wrong. So I could test that to see if it actually works. So you're always going to do an if-then statement to make up your hypotheses, okay? More on hypothesis in just a minute. Okay, so we said that, or I said, there's more on the hypothesis in a second. And this is what I need to talk to you about first. The problem, Okay? Your hypothesis has to relate back to the problem of the experiment. Okay? You could phrase your hypothesis correctly by making it an if-then statement, but it could still be a poor hypothesis or a bad hypothesis because it doesn't relate to your problem. All right? Let's say that our problem relates to the light switch. We'll use the light switch example again, okay? And we want to know if flipping the light switch down is going to turn the lights off. And so you write a hypothesis that says, if the lights turn off, then the experiment is a success. Okay, so you wrote an if-then statement, but I can't test that because I don't know what a success is. That's not something that I can measure. I can't observe that, all right? Or I've gotten hypotheses that say something like, if everything works correctly today, then I will enjoy this lab. All right, that has nothing to do with the problem that we are talking about. So your hypothesis has to relate back to the problem. All right, so let's add that in there somewhere over here next to it. Must relate to the problem. All right? Next, we're going to talk about theories, okay? Unfortunately, in society today, people add just a in front of the word theory. They'll say, oh, that's just a theory. And when they do something like that, the rest of people become accustomed to hearing it, and they start to relate the word theory to a guess, to somebody's just guessing about something. That's not what a theory is, okay? A theory has been proven, and it's not been proven just one time. It's been proven over and over and over again by every scientist that's ever tested it, okay? So you can't just ignore a theory and what it says because you don't like what it says, all right? If there was even one scientist, one person in the whole world that ever proved that theory wrong, then the entire community would have to throw it out and we would need to adopt a brand new theory, okay? The reason that theories still exist is because they've never ever been proven wrong, not one single time. And as the years progress and we get better and better technology, telescopes that can see further into space and methods of dating things more accurately, we go back and we retest things we've already tested just to make sure that we were right, all right, that what we said is true. Because maybe we only thought it was correct because our technology wasn't good enough to see what was really going on. And so when we get new technology, we go back and we test again, and the theory is proven right again. So over and over and over again, it's been proven correct. So we can't just ignore it. It is going to be accepted as fact in the science class. All right. Now theories talk about something specific. All right. They are over one single topic. All right, like the Big Bang Theory. Okay. But a law is over a broad topic, all right, like the law of gravity or the law of conservation of energy, okay? Energy was in your biology class, all right? The sun provided energy for the plants provided energy for the animals, okay? Energy is going to be in this chemistry class also, and energy will be in your physics class when you take that. So energy is a big broad topic. It's more general, and so that's why it's a law. Laws also have to be able to be proven mathematically, all right? So let's write that in there. Are proven mathematically. All right, now let's talk about models, okay? Models have to be able to predict something, okay? When we have a model of an atom, that helps us to predict how many electrons are in the atom, or Or would this atom be capable of bonding with another atom? Or we could replicate, an ecosystem, and then we could introduce something new into the ecosystem and see if things start dying off. And if they do, then we could apply that to the real world, and we could say, if this thing gets into, there's some kind of a fish that's from Australia that's being introduced into a lake that it's not supposed to, and they figured out that if it gets into that lake, that it will become the dominant species and it'll kill out all the other fish in that lake. Okay, that they made a model to do that with first and predict that that's what would happen, and then that fish has started making it into that lake, and they're starting to see that they were right. So now they're putting up these big grates and all these things underneath water to try and keep the fish out of the lake that they're not supposed to be in. That's a kind of general description. Then we've got phenomena. Really, a phenomena is anything that you can observe. All right, so you look around your house or look outside your window and it's stormy or whatever. That's a phenomena. Okay, so it's something happening in nature. All right, let's do a quick math review here. From your algebra class, you should remember that when you are multiplying things of the same base, and in this case we're going to say the base is centimeters. If you're multiplying things of the same base, then you can add their exponents. So here I'm doing centimeter times centimeter times centimeter. Well, anything can be raised to the first power and still be itself. So this is really centimeter to the first power, and so is this one and this one. So we will have centimeters cubed because we can say 1 plus 1 plus 1 over here. That's our unit. Now if we looked at our numbers over here, we would be saying for this specific box, 1 centimeter times 1 centimeter times 1 centimeter. Alright, well 1 times 1 times 1 equals 1. And then centimeter to the first times centimeter to the first times centimeter to the first is going to be centimeters cubed. So the volume, because this is the formula for volume, length times width times height, the volume of this box is 1 centimeter cubed. And there's a conversion factor in the metric system video that you need to watch that says that 1 centimeter cubed is equal to 1 milliliter. So that means that if I filled this cube here up with water, let's say, and I filled it all the way up to the brim with water, and then I got myself a graduated cylinder, and let's say that the 1 milliliter mark is right here, and I poured that water into the graduated cylinder, it would fill it up right to that 1 milliliter mark because these things are equal to each other. Okay? Let's talk about density since we're talking about water here real quick. Density has what we call a derived unit. A derived unit is a combination of the normal SI units, and if you don't know what I'm talking about, we're going to handle that in the metric system video, so you need to watch that, or you should have already watched it, and if you haven't, just go watch it. Alright, so a derived unit is a combination of any of the normal SI units. Density has a derived unit, grams per milliliter. Alright, grams is a SI unit all on its own, and milliliters are an SI unit all on their own, and together they create a derived unit. You need to know that the density of water is equal to 1 gram per milliliter. You'll need to know that for the rest of your life. And that the formula for density, hopefully you remember this from your biology class, density is equal to mass divided by volume. Alright, also density allows things to float or sink, alright, or at least it's a contributing factor. So if we look here, we've got some ice floating in water. The reason that ice floats in water is because ice is less dense than water. Okay? And so it floats on top. But if we look over here, we can see got a couple of pennies that have sunk to the bottom of the liquid in this measuring cup. The reason for that is because the pennies are more dense than the liquid that they're submerged in. Okay? And if we had something that was exactly the same density as the liquid that it was in, then it would kind of float halfway in there. All right? So with that being said, let's answer this practice question. A sample of aluminum metal has a mass of 8.4 grams. The volume of the sample is 3.1 centimeters cubed. Calculate the density of the aluminum. Alright, so the first thing that you're going to need to do is get your formula for density. Alright. Now let's identify what we have. The 8.4 grams is our mass. Alright, the 3.1 is our volume. So really all we need to do is just plug those numbers in where they belong. The mass was 8.4 grams and the volume was 3.1 centimeters cubed. So in your calculators you're going to do 8.4 divided by 3.1. And when you do that, you're going to get 2.709677742. Okay, now right now this is what I call a naked number. And I do that because it doesn't have any units with it right now. The units are these guys right here. The units for density are grams per centimeter cubed. Or they could be grams per milliliter. Well, what's the difference between grams per centimeter cubed and grams per milliliter? Alright? Centimeters cubed are the units when the object is a solid, and milliliter is when the object is a liquid. So back here on this one, we really should say that this is the formula for the volume of a solid. Volume of a solid. Alright? So that we could measure the length, and we could measure the width, and we could measure the height. And we would measure that with a meter stick. Alright? So our measuring device there would be a meter stick for a regularly shaped object, like a cube or a rectangle or something like that. Alright? So those are for solids. Now if we wanted to get the volume of a liquid, then we would use our graduated cylinder over here. That's what we get the volume of liquids with. Okay, meter stick, and this formula over here is what we get the volume of a solid with. And so if we're trying to get density of something, and it's the density of a solid, then the units are going to end up being grams per centimeter cubed. If it's the density of a liquid, then they're going to end up being grams per milliliter. Alright, that's all I've got for this lesson. Please make sure that you go on forward and watch the lesson for the metric system, and that you watch the lessons over significant digits and scientific notation and all of that stuff. Alright? Thank you for learning with me today, and I will see you next time.